Let's take a look at another synthesis question from the first quiz on chapter 13, so quiz 13. So if we want to go from cyclohexene to 1-methylcyclohexene, how would we do that? Well, there's no way to functionalize the compound just by doing something to this proton here. There's nothing we can do with that. But we can do something with an alkene in a molecule. We know that we can do something with an alkene. So what if we just started out by treating this with dilute sulfuric acid? If we use dilute sulfuric acid, what we're going to end up with is this secondary alcohol. Now it's starting to look like something that we could manipulate in some way. But we need to be able to install another carbon, because in this molecule we have 6 carbons, and in this molecule we have 7 carbons, and we're probably going to do that by Grignard chemistry. In Grignard chemistry, if we use our Grignard chemistry, the only things that we know how to add a Grignard reagent to are aldehydes, ketones, and esters. So the way we're going to do that is we're going to convert this molecule into a ketone. So how would we convert that into a ketone? Well, there's several reagents that you could use. A lot of students chose to use sodium dichromate, sulfuric acid, and water. So what this does is it makes chromic acid, and it will convert this secondary alcohol into a ketone. Now you have a ketone, and this is something that you could use to react with a Grignard reagent. So we only need to add 1 carbon, so 1 methyl group. So if we, let me just erase that. So if we treat this with methyl magnesium bromide, and then with water, as we always do after a Grignard reaction, what's going to happen is the anion from that methyl group, it's going to be nucleophilic enough to come in and attack that carbon, so that we're going to end up with a tertiary alcohol. So we're going to convert this into a tertiary alcohol. So we'll have our OH and our methyl group here. Now we're getting even closer. So basically what we need to do is we need to convert this hydroxyl group into a good leaving group, and then do some kind of dehydration or elimination mechanism so that we can regenerate that alkene. So what we need to do to convert that into a good leaving group, the first thing we're going to do is we're going to treat that with tosyl chloride, and pyridine. I hope I don't run out of room here. But what you're going to end up with then is you're going to have OTS and your methyl group. So to get from here to here, and this is probably tricky for a lot of people, but hopefully you would remember from first semester, is that we're trying to make the most substituted alkene. Okay, there's 2 possible alkenes that we could make here. We could make either the one that I have shown in red or the one that I have shown in green. But in order to make the one in red, this is the most substituted, and the one in green is the least substituted alkene. So in order to make the most substituted alkene, I'm going to use a non-hindered base. So I'm going to use sodium ethoxide, and that will pull this proton off. What happens is your ethoxide anion will come in here, and it's going to pull this proton off, regenerate your double bond, and you will lose your leaving group, the tosylate, to give you the desired compound in red. If you wanted to go from here and make this less substituted alkene, what you would do then is you would treat it with potassium T-butoxide, which is a hindered base, which will pull off the proton from the methyl group. And I'm not going to draw that mechanism out, but hopefully this will give you an idea of how to solve this kind of problem. And what I would recommend doing is looking over chapter 12 and reviewing all of the reactions that you would have learned first semester, because we're going to learn a lot more new reactions this semester.